Okay, so we were talking about the ideal gas law. I had just introduced you to the formula for it, and now we're talking about the ideal gas constant. This ideal gas constant is represented by the variable R, and as long as you have your pressure in the units of atmospheres, your R is always going to be 0.0821. This number you need to memorize. Okay, so you will always use 0.0821 for R as long as your pressure is measured in atmospheres. If your pressure is measured in anything other than atmospheres, you would have a different R. So if you're measuring in kilopascals, then your R would be 8.314. If you're measuring in millimeters of mercury, your R would be 62.4. You don't have to memorize those two numbers. If you needed to use one of those two numbers on a test, I would give it to you as in a statement, R equals this number. You just would need to know what to do with it. However, this 0.0821, you do have to have memorized. All right, let's try a practice problem. So this problem is asking us to calculate the number of moles. Remember, that's our lowercase n. Contained in 3 liters, that's going to be our volume, at 3 times 10 to the second Kelvin, that's our temperature, with a pressure of 1.50 atmospheres. So all we have to do is remember what our ideal gas law formula is. It's PV equals nRT. Now we just plug in what we know. Our pressure is 1.5 atmospheres. Our volume is 3 liters. We don't know what our moles are. That's what we're trying to calculate. R is that gas constant I just talked about. Remember, because our pressure is atmospheres, R then is 0.0821. And then our temperature is 3 times 10 to the second Kelvin. Remember, just like all the other gas laws, your temperature has to be in Kelvin. 3 times 10 to the second is the same as just saying 300. So I'm going to write 300. Now you use algebra to solve for n. Some people multiply this out together first before they divide. I just divide all at the same time. And you can do that too. Because notice 300 over 300 is a giant 1. Same thing with your r's. And then you just divide over here by the same numbers to keep things even and equal. Now when I plug it into my calculator, I'm going to plug in 1.5 times 3 divided by 0.0821 divided by 300. Remember, you can't say times 300 or that pops it up into that numerator. And when you do that, you get that n equals 0.183 moles. And that would be how we would work an ideal gas law problem. Okay, so now let's talk about this idea of what an ideal gas actually is. Ideal means like the best case scenario, almost perfect, what we theoretically think it should be. Although that doesn't always match up with what reality is. So let's look at this. Ideal gases follow the kinetic molecular theory. Right? So they act the way that theory that we talked about last chapter says that they're going to act. Ideal gases have no intermolecular attractive or repulsive forces. So they're not attracted to one another and not repelled from one another. The particles are in constant random motion. Their collisions are perfectly elastic. If you remember from last chapter, that means no energy is lost when they collide. These are the three things that establish an ideal gas. However, this is the reality. No gas is truly ideal. Most behave this way at a wide range of temperatures and pressures, but not at all temperatures and pressures. Real gases deviate the most from this at high pressures or low temperatures. Polar molecules are going to attract and repel one another because they've got those charged areas of them. So there is going to be some interaction between them. Therefore, polar gases do not behave like ideal gases. And the larger a gas is, the larger that molecule is, the less it behaves like an ideal gas. So those are some things to keep in mind as far as the differences between them. However, any problem I give you, you can assume it's an ideal gas. That's fair for this class. And that's our end for the lesson. You do have one more video that shows you some demonstration problems in using this ideal gas law. I hope you have a great day. I'll look forward to seeing you via the video on Friday, in the Zoom meeting if you've got any questions or problems, and then definitely in our class meeting next week. Hope you guys have a great day. Bye-bye.